Okay, so now I'm going to talk about the hot air balloon problem again, but I'm going to do it algebraically. So we've got, again, a hot air balloon that is ascending. A sandbag cuts loose and falls to the ground. It takes a certain amount of time for it to ascend before they cut it loose, and we want to figure out how much time it takes for it to get back to the ground in terms of how much time it took to get up. So a quick sketch of the motion of that balloon and the sandbag. So this is position and T. The balloon ascends. Sandbag cuts loose. Sandbag keeps going up for a while at initially the same velocity that it had before it let go, turns around, and then comes back down to the ground. And what we're trying to figure out is, supposing that it was delta t time before it let go, how much more time is it going to take to get to the ground? All right, so we're going to write down some equations describing the position of the balloon on the way up and the position of the sandbag on the way back down. So we've got position on the way up is x initial plus vi t plus 1/2 a t squared. And we were told that on the way up, the acceleration was g over 4. On the way down, the acceleration is negative g. All right, the initial position was 0. The initial velocity was 0. And we've got 1/2 g over 4 t squared. So that's the function for the position. But we're also given that it spends delta t in the air before the sandbag is cut loose. So that means that the height that it gets to is 1/2 g over 4 delta t squared. All right, so now we know how high it got. How fast was it going at the moment that it let go? So for that, we want v is the velocity is the initial velocity plus the acceleration times the time. Well, the initial velocity for the balloon was 0 because it wasn't shot upwards. The acceleration was g over 4, and the time that it's ascending with that acceleration is delta t. So that means the velocity at the moment that it starts to fall is g over 4 delta t. All right, so those now give us two initial conditions for our starting point for the downward trip. So this is from the up, but those serve as our starting points for the way down. Okay, so down. So we have another position function, xi plus vi t plus 1/2 a t squared. And the initial position is that height right there. So g over 8 delta t squared. The initial velocity is that plus g over 4 delta t times t. So this is going to be a little bit confusing. So let me put some parentheses around here in a different color. So this delta t is the amount of time that the balloon was ascending before the sandbag started to fall. That delta t is the time of the balloon on the way up before the sandbag started to fall. That t is not. That's the amount of time on the way down. And then we've also got one more term. I'll have to put it right here to fit, plus 1/2 times negative g, negative because now it's falling, and t squared. So this t here and that t there are both times on the way down. The delta t's are times on the way up. All right, so what am I asking myself with this function? If I'm trying to figure out how much time it takes to get to the ground, I'm asking myself, at what moment in time is the position 0? So I'm going to set that equal to 0. 0 equals this expression, g over 8 delta t squared plus g over 4 delta t times t minus g over 2 t squared. All right, well, that's a quadratic formula. That's a quadratic equation. I've got a term squared, a term linear, a term constant, all equal to 0. How am I going to figure out what moment in time makes it true that this whole thing is equal to 0? I'm going to use the quadratic formula. So remember that the general form for a quadratic is ax squared plus bx plus c. So this is the a, that's the b, and that's the c. So I want the time that makes this true is t equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So now I'm going to have to plug all that stuff in, and it's going to get a little bit hairy with this algebra here. So the t is negative b, that's g over 4 delta t, g over 4 delta t, plus or minus the square root of b squared, so g squared over 16 delta t squared, minus 4 times the a, that's negative g over 2, times the c, that's g over 8 delta t squared. All of that gets divided by 2 times negative g over 2. Okay. This is, there's a lot in there. So how are we going to simplify this? So I notice a couple things that might make it a little bit easier to see. I notice that there's a delta t there, a delta t squared there, and a delta t squared there. There's also g squared inside there. So I'm going to try and simplify this radical like this. So g over 4 delta t plus or minus g delta t times the square root of 1 over 16 plus, looks like 4 over 16, 1/4, all divided by negative g. That's what the t has to equal. T is g over 4 delta t plus or minus g delta t. All right, what are we going to do now? I'm going to move this over. I'm going to go kind of sideways. So I got to simplify that radical and combine like terms. So I've got delta t in both terms, and I've got g in all these terms. I've got g, g, and g. That means I can divide out that g. There aren't actually any g's here. So this is the same thing as t equals delta t times 1/4 plus or minus the square root of 1/16 plus 1/4 is 1/4 plus 4/16, that's 5/16. Huh. Isn't it interesting? You can already see that how strong gravity is doesn't really matter here for finding out how much more time it takes. All right. Well, the square root of 16 is 4. So that's going to give me delta t is 1/4 plus or minus the square root of 5 divided by 4. So then I can factor out the 4, and you get delta t over 4 times 1 plus or minus root 5. Okay, which root do I want? Do I want the positive one or the negative one? So the negative one, 1 minus root 5 is like 1 minus 2 something. So that's a negative number. That's going backwards in time. That's on this parabola. That's tracing this backwards down here to when it would have been at 0 if you traced it backwards. That's not actually what happens. We want this one over here. That's the one where you're adding something to that. So 1 plus 2 point something is 3 point something divided by 4 is going to be somewhere around 0.8, which is apparently what we got before. So that is our result. We want the positive root. So the t is delta t over 4 times 1 plus root 5. And if you looked at the other video with the Desmos graph, you can see where I got that formula from to show you graphically where how much time it took to get to the ground. So as I said before, the physical insight here, the most important thing is you've got a constant acceleration up. You use this equation to describe that and figure out what the height is after ascending for that amount of time, what the velocity is after ascending for that amount of time. Then you use those as starting conditions for this moment after the sandbag lets go. The velocity is continuous at that moment, so the initial velocity is the same one that you had right here. The initial position is the same one you had right there. And then you use the quadratic formula to figure out what time makes it true that the position is equal to 0 again, right there. Let me know if you have any questions.